Let's begin our second set of notes in probability. We're going to concentrate on sample space. During this lesson, students will be able to describe events as a subset of a sample space, the set of outcomes, using characteristics or categories of the outcomes, or as unions, intersects, complements, or other events, such as ors, ands, and nots. In our first example, we have Joe and Sarah playing a board game with a spinner. On our spinner, you'll see that there are a set of numbers, 1, 2, 3, 4, spread out along there. Also on the spinner, the sections are colored. There are a certain set of these that are red, and all of those are indicated by the R after each one of the numbers. Each one of these are considered red. You'll see that there are a set of yellows with all of the Y's, and a set of green with the G's, and a set of blues that are left on there. First thing we'll do is answer the question, what subset will we call A of the sample space described in the region above or to the left? In this, we are landing on green. All of those that are green will be this set of items. There's a 1G here, there's a 2G, there's a 3G, and a 4G. Each one of those are green. If you spin the spinner, you might land on a green. That green may be the 1G, the 2G, 3G, or the 4G. If we look at another subset called B, that B, if it's defined as landing on something that is the number 1, let's look at that subset. Anything that, or excuse me, I said number 1, I meant to say number 2. Anything that lands on 2, well, we have a red 2, or 2R. We have a yellow 2, 2Y. We have a blue 2, B2. We have a green 2, 2G. All of those are possible outcomes if we're going to spin it and land on the number 2. The subset of this, in terms of A and B, described when the spinner is landing on a green section with the number 2, would be answered by something that might look like this. It's just going to be the one that has a 2 and is green. The way we would indicate this, it's not supposed to be here, would be a notation that would look like this. We would land on something that's in subset A and subset B. Or in this specific example, something that is green and has the number 2 on it. The last problem is an example of an intersection. In this case, an AND statement is used for intersection. It has to be in both it has to be both green and 2 for it to be in this spot. The intersection occurs when both of those conditions are met. When we have to have this and that, both of those items, that's an AND statement. We've used these in the past, and we'll continue to use them during this unit to help us see intersections, Venn diagrams, because they're great to just look at them and you can quickly notice where you have intersection. Let's take a look at an example here to help us with that. In this first one, we have 50 students, and they were asked whether or not they're taking a foreign language and whether or not they're playing sports. How many of the students are taking a foreign language? That would be all of these. All of those are taking a foreign language. That would simply be the 23 plus 14. 23 plus 14 gives us a total of 37 students in foreign language. How many are playing sports? That's going to be represented by everything inside of here. 10 and 14 for a total of 24. How many are doing both? That's represented by this part of the Venn diagram. They're in both of the circles. The 14 that was in each one of those previous sums is in the amount of students that are in both. How many students did not play a sport and do not take a foreign language? There are 3. That's indicated by this number here. How many students play a sport but do not take a foreign language? All of these are playing sports. This is the group of playing sports that are taking a foreign language. So 10 would be the number of students who play a sport but are not taking a foreign language. A two-way table is similar to a Venn diagram. A two-way table shows data that pertains to different categories. In the Venn diagram above, it was foreign language and sports. In the next one, or this next part of this is going to take that data and substitute it in here. So let's fill out our Venn diagram. Well, one piece of information that we know is that there were 50 students. So our total here must be 50 students, no matter how we separate these numbers. An easy number maybe for us to see is the 14. The 14 corresponds to those who are in this column, play sports, and this row, taking a foreign language. Then the 10 students here are in the column that says they are playing sports, but they're in the row indicating that they do not take foreign language. That total is 24. That's the same amount and same calculation we did up here in Part B. If we look at the students taking foreign language, we've already included the 14 that are both in sports and taking a foreign language. Now what we need to do is put in here the 23 students that are in a foreign language but not playing sports. We add those up, we'll get 37. 37 was the same calculation we did up here. Not in sports, but taking a foreign language, in sports, and also taking a foreign language, 37. Then the 3 represents those students who are not in sports and not taking a foreign language. Let's do some addition. 13 here, 13 plus 37 is 50. 26 here, 26 and 24 gives us 50. With our our two-way table, we can quickly do some probability calculations as shown here. What's the probability of selecting someone at random who's taking a foreign language and in sports? Foreign language and in sports are these 14 here, out of the 50 students who were considered in this, which does simplify to 7/25. What's the probability of selecting someone at random who is not taking a foreign language and in a sport? So in a sport is here, not taking a foreign language would be 10 out of the 50, which simplifies to 1/5. What's the probability of selecting someone at random who is a foreign, it says is a foreign language, it should say is taking a foreign language, is taking a foreign language from those who are in sports. You recall, this is a conditional probability. From those who are in sports says The only ones we're going to consider are the ones in this column here. From those in sports would have to be these. Remember, we did this example in class before where we said we asked a question, a clarifying question, and those people stood up. So this would be like saying all 50 people in the room, which one of you are in sports? 24 people would stand up. That becomes our denominator because they met the condition. That's the conditional statement that must be met before we can then say, all right, which one of you are taking a foreign language? And indeed, 14 of those 24 standing would raise their hand, and we'd get 14 out of 24, or 7/12 as the probability of getting those. Let's take a look at the next one. What is the probability of selecting someone at random who is not in sports from those who are taking a foreign language? Different question, but same idea. This time, everybody's sitting down, and we say, if you are taking a foreign language, please stand up. The number of people who stand up, you'll see, are the 37 here. 37 becomes our denominator. What's our numerator? Well, let's look at what it's asking. It's saying we are going to find a person who is not in sports only from those who are taking a foreign language. And that would be 23. 23 37s is the probability of selecting someone at random who is not in sports. Let's take a look at our next problem. In this one, we've got a manager at Adventure Park, and he's offering a free round of mini golf for each person today. He's hoping that people will then also purchase tickets to go on the go-karts and laser tag. He keeps track of 50 customers who played mini golf. He records that information over here. Let's see and analyze his data for him. Okay? If another person plays a round of mini golf, determine the probability that that person will do these. So based upon his data, that next person, what's the probability that they'll do this? Purchase tickets for go-karts. Purchase tickets for go-karts would be all of these inside of here. All of these people purchase tickets for the go-karts. That would be 20 plus 15, or 35, out of the total 50 customers that were sampled. Next, what's the probability that the next person, based upon this data, will not purchase tickets for go-karts? Well, let's think about what that is. These were all go-karts, and remember, not purchase, wouldn't that be an easy subtraction problem like we did yesterday? A not purchase simply is taking 50 out of 50 and subtract the ones that did purchase, and that's going to give us 15 out of 50. To check your work, we could have done this one another way, but I just wanted to make sure you see that subtraction problem since we did that yesterday for our knots. We could also just look and see that there were 11 who only played mini golf. There were 4 that played miniature golf and purchased laser tag but didn't go go-karting. That would have been 4 plus 11, or 15/50 as we calculated. Let's take a look at the next one. What's the probability that someone will purchase a laser tag ticket? Well, laser tag is represented by this circle. So 15 and 4 will give us 19/50 will be the probability of someone purchasing laser tag. Let's do another knot for this one. Same way we did before. Excuse me. We'll take 50 out of 50 and then subtract this 19 out of 50. which will give us a total of 31 out of 50 who did not purchase tickets for laser tag, which also could have been done by adding the 11 and the 22 together. Part E of this problem says, what's the probability that selecting the next person that that person will purchase tickets for go-karts and laser tag? Go-karts and laser tag is this set right there, 15 out of 50. What's the probability of purchasing a ticket for go-karts or laser tag? Well, purchasing tickets for a go-kart, we answered up here. That was 35 out of 50. Laser tag, we answered here in part C, and that was 19 out of 50. We can add those two together, and that's going to give us a little bit more than what we bargained for, because adding those together, we end up getting something that looks kind of weird. 35 plus 19, that's over 50. Can we get something that's over 50 as a probability? No, because we have a dilemma here. Purchasing tickets for go-karts or laser tag, both of those included these 15 that did both. So this is a case where these are not independent events. And what we need to do is subtract the 15/50ths that occurs when we counted the 15 in here with the go-kart and that same number here with the laser tag. Now what we end up doing is adding these together, and yes, we get a number over 50, but then when we subtract 15 from that number, we get 39 out of 54, and that will include all of these. Another way of checking this would be, that's going to be 20 plus 15 plus 4 for a total of 39. 20 plus 15 plus 4 out of 50 will give you the same answer. And then finally, what's the probability that the person will not purchase any tickets, but just go in and get the free mini golf or miniature golf? That's the 11 out of 50. Now, next one. In this case, we have a two-way table, and we're going to take that two-way table and fill out a Venn diagram. You should be able to go from Venn diagram to table, table to Venn diagram. So, one that's kind of obvious is the cake and ice cream. At Nikki's party, there were 8 people who asked for cake and ice cream. Next, let's do the 6. 6 were people who had ice cream but no cake. Had ice cream but no cake would be 6 here. Next, let's see what we have here. This appears to be those who have cake but not ice cream. Cake but not ice cream are those 3 here. And then finally, the 4 that have no cake, no ice cream are these guys here. That's 4. Now, one thing you will want to do is always total these up. We've got 11, 10 for a total of 21. There were 21 people at Nikki's party. 7 and 14 are the total of wanted ice cream and no ice cream, which also added to 21. Okay? Next, a group of U.S. history teachers asked students where they would rather go for an overnight field trip. Here are their results. In this two-way table, we don't have all the information. So we've got to figure out from just this, there's nothing up here that we can use to supplement this. We have to look in here and figure it out. Washington, D.C. had a total of 97, which means 20, if there were 20 girls who chose D.C., then 97 minus 20 would give us 77 boys who chose D.C. If there were 95 girls total that answered the questionnaire, and 20 of them said Washington, D.C., 95 minus 20 would mean that 75 girls wanted to go to Williamsburg. Add this column, we get 103. 97, 103 gives us 200. Add 77 and 28, we get 105. Does that check out? Yes, 105 plus 95 equals 200, and we're done with our two-way table. Next, what percentage of students would rather go to Washington, D.C.? There is no clarifying statement. There is no condition here. It's all of the students of 200. And out of those would rather go to D.C., 97 out of 200, which would simplify to 43.7%. What percentage of the boys would rather go to Washington, D.C.? What percentage of the boys is implying a conditional statement? It means that we're only going to look at the boys and evaluate those. What percentage of the boys? Percentage of the boys would be 77 out of the total 105 boys, which means 73% of the boys would rather go to Washington, D.C., which means that the decision to go to Washington, D.C. is not independent of whether you are a boy or a girl. Boys are more likely than the total probability to choose Washington, D.C. If this one was 43.5 to match the overall, then boys choosing D.C. or girls choosing D.C. would be independent of each other. What percentage of those who'd rather go to Williamsburg are girls? So in this case, it's implying a conditional statement of those who'd rather go to Williamsburg, meaning this group here. Of those who would rather go to Williamsburg, there are only 103 that were choosing that. What percent of those are girls? It would be 75 out of 103, or 78.9%. Next, we're going to look at a table and use that table to answer questions. This one actually has more than just two categories in rows. There is not a limit to the number of columns or rows that you can have in your two-way table. Two-way just means that there are columns and rows. So what's the probability that a random selected male has brown eyes? Randomly selected male has brown eyes means we're looking at just the males. Randomly selected male is the conditional statement. Once we've met that condition, we'll look in here and see that there are indeed 38 out of 80 males who have brown eyes. What's the probability that a randomly selected female has green eyes? Randomly selected female is the condition that we must meet, which means our denominator is going to be 100. Then we look in that column for green eyes. Green eyes, 14 out of 100. The probability of selecting someone with blue eyes is a male. Blue eyes is the conditional statement. We're not asking what's the probability that someone has blue eyes and is male. It's saying if we're looking at blue eyes, which is this row right here, that gives us a denominator of 22. And then, after that condition is met, we're looking for the males in that, which gives us 10. Next one says the probability of random selecting a student with green eyes is female. Green eyes is females. Green eyes is the condition that must be met. Once we've met that condition and got our denominator of total green eyes of 26, then we evaluate those 26 and find that 14 are female. The probability of the random selected student that does not have green eyes is male. Does not have green eyes is male. Well, do not have green eyes would mean everything except the 26. And again, randomly selecting person that does not have green eyes is our condition that we must meet. Well, there were 180 total students. 26 had green eyes, which means there were 154 students who do not have green eyes. That is our denominator. That is the condition that must be met. Before then, we look and see how many of those were male. We can also do a subtraction. Not problems are sometimes a lot easier with subtraction. There were 80 total males. Of those 80 total males, 12 of those had green eyes. 80 minus 12 gives us 68 males who have green eyes. Okay. So again, all we've done was take out this column here for does not have green eyes. After we took out that column, we considered all of the numbers left, or excuse me, that row, all of the numbers left, which gave us 54. Then we looked at this column of males, and since we didn't include those who have green eyes, not green eyes, we subtracted 12 from the 80 and got 68. Next, the probability that a randomly selected person has brown or green eyes. This is not a conditional statement. This is just saying, hey, let's find out how many have brown, 82. How many have green, 62. Within or, we add them together, and it's out of the total 180 students. 82 plus 26 gives us 108. These are independent of each other. We can't have someone with brown and green eyes according to this data. Someone may have, and we know that that does occur, where people have one eye, one color, and one the other, but that would be considered in this other column. So we don't know for sure about those. But there isn't a case where they are counted twice, so we don't have to subtract anything from those. Lastly, the probability of randomly selected person, that is female. That is female is the conditional statement here. So that 100 females becomes our denominator. Has blue or green eyes. Blue eyes out of the females, 12. Green eyes out of the female, 14. Add those together, 1200s plus 1400s gives us 2600s. Hopefully this made sense for you. Please go ahead and take time now to do your exit quiz. Once you're done with your exit quiz, go ahead and start and finish your homework. Have a good day.